For 25 years, cosmologists have been telling us exactly how the story ends. It was supposed to be a lonely, quiet death. We were told that the universe would expand forever, driven by an invisible force pushing galaxies apart faster and faster until the stars burned out, the black holes evaporated, and the cosmos faded into an infinite frozen dark. They called it the Big Freeze. It wasn't just a theory, it was the accepted fate of everything that exists. But in the last few months, that certainty has been shattered. Deep in the data of the largest 3D map of the universe ever created, scientists have found something that shouldn't be there. The invisible force driving our expansion, dark energy, was supposed to be a constant, unchanging, eternal. But the new numbers suggest it is doing something impossible. It is changing. It is weakening. If these findings hold true, the standard model of cosmology is broken, and the universe isn't heading for a freeze. It is slowing down. And if it slows down enough, it might just stop, turn around, and collapse in on itself. We are no longer looking at an infinite dark. We might be looking at a fiery end. To truly grasp the magnitude of this potential discovery, we must look at the foundation it threatens to crumble. The story of our universe's fate has been rewritten before, and every time it happens, it shakes physics to its core. A century ago, Albert Einstein added a term to his equations of general relativity called the cosmological constant. He denoted it with the Greek letter lambda. At the time, he did it to force the math to match the belief of his day, that the universe was static, neither expanding nor contracting. When Edwin Hubble later proved the universe was actually expanding, Einstein called lambda his biggest blunder and threw it away. But in 1998, the blunder came back to haunt us. Two independent teams of astronomers studying distant supernovae, exploding stars used as cosmic mile markers, realized that the universe wasn't just expanding, it was accelerating. Gravity should be pulling everything together. It should be acting as a cosmic brake. But something was hitting the gas pedal. Physicists resurrected Einstein's lambda to represent this mysterious, repulsive energy of empty space. We called it dark energy. Since then, the Lambda-CDM model has been the standard model of Big Bang cosmology. The lambda stands for dark energy, and the critical assumption of this model is that dark energy is a constant property of space itself. Whether you are in this room or a billion light years away or 10 billion years in the future, a cubic meter of empty space should have the exact same amount of repulsive energy. It is this constancy that condemns us to the big freeze. If the engine never stops and the gas pedal is glued to the floor, there is no other outcome. The universe tears itself apart. But science does not deal in dogmas. It deals in data. And for the last few years, the data has been getting messy. We have entered the era of precision cosmology. We are no longer looking at fuzzy images of stars. We are mapping the skeleton of the cosmos. The primary weapon in this new fight for truth is DESI, the dark energy spectroscopic instrument. Situated atop the Nicholas U. Mail telescope at Kitt Peak National Observatory in Arizona, DESI is not a traditional camera. It is a time machine. Its focal plane is packed with 5,000 swiveling robots, each carrying a fiber optic cable. These robots can independently target individual galaxies with microscopic precision. By capturing the light from these galaxies and breaking it down into a spectrum, DESI can calculate exactly how fast they are moving away from us. But DESI isn't just measuring speed, it is measuring history. It uses a phenomenon known as baryon acoustic oscillations, or BAO. In the first 380,000 years after the Big Bang, the universe was a hot, dense soup of plasma. Sound waves, actual pressure waves, rippled through this fluid. When the universe cooled, those ripples froze in place, creating slightly denser regions where galaxies would eventually form. These frozen ripples act as a standard ruler. We know exactly how big these ripples should be. By looking at how big they appear on the sky at different distances, meaning at different times in history, we can measure exactly how much the universe has expanded over the last 11 billion years. This allows us to reconstruct the history of dark energy. We can see if it has always been the same strength or if it has evolved. This is where the paradigm shift begins. When the DESI collaboration released their first massive dataset, they combined their map with data from the cosmic microwave background and supernova studies. They were looking to confirm the value of W, the equation of state for dark energy. In the standard model, W must be exactly 1, a straight flat line across the history of time. But that is not what the computers spit out. The data prefers a model where W is changing. Specifically, the data suggests that in the early universe, dark energy was pushing harder than it is today. Over the last few billion years, its influence seems to have waned. The density of this vacuum energy is dropping. If you visualize the expansion of the universe as a ball thrown into the air, the standard model says the ball has a rocket strapped to it that never runs out of fuel. It accelerates upwards forever. The DESI results suggest the rocket is sputtering. It is still moving up, and it is still moving fast, but the thrust is dying. This concept is known as dynamical dark energy, or sometimes quintessence. It implies that dark energy is not a constant property of space, but a fluid or a field that permeates the universe. A field that can thaw, evolve, and dissipate. The implications of a weakening dark energy are profound. It changes the timeline of eternity. If dark energy weakens enough, it could eventually drop to zero. If that happens, the cosmic acceleration stops. But it gets worse. Some models of dynamical dark energy suggest it could cross into negative values. Instead of pushing gravity away, it would begin to assist it. This triggers the scenario known as the Big Crunch. Imagine looking at the night sky billions of years from now. For eons, astronomers would have seen distant galaxies moving away. Their light shifted to the red part of the spectrum. But slowly, the red shift would stop. The galaxies would seem to pause, and then they would turn blue. Gravity, the relentless sculptor of the universe, would finally win the tug of war. The expansion would reverse. The process would be slow at first, but it would be exponential. As the universe contracts, the background radiation left over from the Big Bang, which is currently a frigid 2.7 Kelvin, would begin to heat up. The cosmos would become a pressure cooker. Eventually, the universe would shrink to a size smaller than our solar system. But containing all the matter and energy that ever existed, stars would not just collide, they would be cooked from the outside in as the temperature of space itself rose above the temperature of their surfaces. Atoms would shatter, black holes would merge, everything would collapse back into a singularity, a point of infinite density. Some theorists even suggest this could lead to a big bounce, where this crunch triggers a new Big Bang, creating a cyclical universe that breathes in and out for eternity. However, we must step back from the edge of the abyss. The scientific method demands skepticism, especially when a discovery threatens to overturn decades of established physics. In the world of particle physics and cosmology, a discovery is only considered definitive if it reaches 5 sigma confidence. This means there is only a 1 in 3.5 million chance that the result is a statistical fluke. These current findings from DESI, combined with other datasets, sit in the range of 2.5 to 3.9 sigma. In the scientific community, this is effectively a flashing yellow light. It is incredibly compelling. It is strong evidence, but it is not proof. We have been here before. We have seen signals that looked like new physics, only to realize later that they were caused by dust in our own galaxy, or a loose cable in an experiment, or simply a rare statistical coincidence. The universe is a noisy place, and extracting a clean signal from billions of years of chaos is the hardest thing humans have ever attempted. Furthermore, changing the standard model doesn't just fix the future, it breaks the past. The Lambda-CDM model has been incredibly successful at explaining everything from the clustering of galaxies to the ratio of hydrogen and helium in the universe. If we throw out the constant, we have to make sure the new variable model still fits all the other pieces of the puzzle. We are currently living in a moment of suspension. The DESI instrument is only partway through its 5-year survey. What we have seen so far is just the first year of data. As you watch this, the robots on that telescope in Arizona are moving, locking onto new targets, gathering more light. Soon, they will be joined by the Euclid Space Telescope and the Vera C. Rubin Observatory in Chile. This triad of next-generation instruments will corner the truth. Within the next few years, the data will either evaporate, returning us to the cold certainty of the Big Freeze, or it will harden into a discovery that wins Nobel Prizes and rewrites the history of everything. We are either living in a universe that is dying a slow, cold death, or one that is holding its breath before the great collapse. Both endings are terrifying in their own way, but knowing which one belongs to us is the ultimate goal of cosmology. The universe is far stranger and perhaps far more temporary than we ever dared to Imagine, as we wait for the final verdict from the stars, one thing is certain: the era of assuming we know the answers is over. If you want to stay updated on this unfolding mystery and other breakthroughs in our understanding of the cosmos, make sure to subscribe and hit the bell icon. The story of the universe is changing, and you won't want to miss the next chapter. Thanks for watching.